Number 44. The naturally occurring charge on the ground of a fine day out in the open country is -1. I'm not sure why I went a little southern there, but anyway, -1, because how else would you say open country, right? You can't open country. All right, big deal. You got to open country, right? It doesn't sound the same. I would agree. Sure, it's this. Letter A. What is the electric field relative to the ground at a height of 3 meters? All right, so nowhere in your book is this formula, I don't think. Or maybe it's in the next chapter. I no idea. Anyway, in order to do this, you need to basically know this formula. The electric field at a certain distance relative to an infinitely charged sheet is basically equal to the sheet density divided them by 2 times then the permittivity of free space. I'm just going to do it out, okay? So basically they gave us the sheet density. That's the charge per square meter. Now what they gave us though was in nanocoulombs per square meter. We know we need that in coulombs per square meter, so I already kind of converted that over here. So it's basically going to be 1 times 10 to the -9. That was, coulombs per meter square. Then divided then by the 2 times then that permittivity of free space, which this is a constant, okay? It's 8.85 times 10 to the -12, and we're just going to calculate, all right? Units, who cares, whatever. This, I don't know how you're expected to kind of do this at this stage, but so anyway, divided them by 2 times 8.85 times 10 to the -12. And this works out to be about 56, right? 56.5-ish. Okay, so that is then the electric field. All right, great. Letter B, then it says calculate the electric potential now at this height. So if we know the electric field and we know a distance and we want to calculate the potential, we use this formula that the voltage, the potential difference between 2 points is basically equal to that electric field, which we're assuming to be constant everywhere, and then multiplied by the distance. So we know that, we're at a particular height above this, little infinitely charged sheet. The height here is going to be 3 meters. So all I have to do is basically just plug in the values, right? The electric field was 56.5. The distance there was 3. And let's just do that multiplication out. And what do we get? About 169 or so. 169. Great. And what's the last part? So to see, sketch the electric field line, sketch electric field and equipotential lines for this scenario. Okay, so remember they always point towards the negative charge, so I guess they're going to be pointing directly down, right? The equipotential lines, I don't know how to really show. It's going to be a little hard because, like equipotential lines, it's a 2-dimensional paper. I'm trying to view this in a 3-dimensional space. It'd almost be like here's the infinitely charged sheet. Make it even smaller, right? We're kind of taking a side view. The lines are pointing down, the electric field lines. Why? Because it's negative. All right, one more. And then the the equipotential line, so anywhere with a constant radius. So I'm trying to show you like a cross section right there, here, etc. Wherever the radius is constant. So this height is constant, that height is constant along every part of this particular circle. Something like that. All right. Anyway, as you can see, I'm definitely not a Bob Ross. So, okay. That does it, guys. Thanks for tuning in. Appreciate it. And we will see you soon. Take care.